Good evening, everyone. So yes, my name is Diego, and I'm Argentinian originally. Did a few trips around the world, but basically I studied in Argentina, uh, my undergraduate level studies, and then I got a PhD position in the Netherlands, in Amsterdam, where I did my PhD and worked for some time. And then about 8 years ago, I got a fellowship of the Royal Society. Uh, it's called the URF. And that's why the Royal Society is here, because they are paying for my salary, or they were paying actually until October. So I got a permanent position here as an associate professor right now at the University of Southampton, and I'm staying there for the time being. Let's see what happens in science and research. You never know where research will take you. But for now, I'm staying here, and I don't have plans of moving, but we will see. So I'm going to talk about the most compact, heavy, and extreme stars where we can still see the surface. And that's the most important thing, because the next step is the black holes. And today we're not going to talk about black holes. We're going to talk about just what didn't manage to be a black hole. And by the way, I don't know which rules you use, but I'm happy if anyone has a question at a certain point to stop and I answer and I continue, or all the answers at the end. I don't mind. So the problem in astronomy is that actually we get lost into the numbers. So I'm going to give you, I want you to actually really think about what you would do in certain situations, and you will understand why later on. So the question is, if you had enough money, a lot of money, what would you do? So you enter a price, and we're going to go into power of 10, and you got $1. So you got $1 or a pound. This is in dollars, but of course, imagine in pounds. You go and buy candies. Not much you can do. You cannot even buy a liter of milk right now. If you get 10, then suddenly you can buy a bit more. This is just a picture of something that is called alfajores. That is some typical sweet from Argentina, and I like to put this picture. Suddenly, if you got 100, well, you can think of something a bit bigger or a bit more expensive, so a good astronomy book or something else. But still, 100 is not a lot. 1,000 starts to be interesting. You have many more possibilities of what you could do with $1,000 or £1,000. Suddenly, if we go with another zero, 10,000, then you can think of a used car. So we are getting into very interesting area. 100,000, so which is 1 0 more, and you can basically pay part of your mortgage or your full mortgage, depending on how bad the situation is. You get another 0, 1 million, and I can imagine that some of you are already smiling. You have a lot of possibilities. Still today, for 1 million is not, it is a lot, but compared to the movies that were 20 years ago, where they stole the bank and they stole $1 million, and it was kind of like they were done for the rest of their life. Now 1 million is not that much if you compare. Now, if it's 10 million, now you buy the house you want, you go anywhere you want, and you will have a lot of money, but be careful, you can still spend a lot. Spend it very fast. Now, 100 million, 10 to the 8, it's already a huge number. And you're going to have trouble, spending this money in things that you can see materialize. Unless you go to buy an island, 100 million is a lot. And I don't know you guys, but for me, I start to lose the idea of how real that number is. Up to 1 million, I can imagine what I would do and how much things cost and how many of those things I could buy. 10 million, I start losing an idea. 100 million, I really kind of like, I don't know, it's like you could buy anything. You get to 10 to the 9, 1,000 million or a billion, as it's in English, and it becomes just completely unrealistic in the sense of it's like if you have power to do whatever you wanted. It's how do you spend that? You have to go to the 10 billion to actually be like Branson, and you realize that it's the number already for me, and again, I don't know you, it doesn't mean anything. It's just like whether you have a pass to do whatever you want or you don't. It's like that. And 10 to the 11, it's even more. So you see the point. That what the message here is, the power of 10, just adding 1 0 to each number at the beginning does make sense, and at a certain point it stops making sense, and at least that's the case for me, and that's why I bring it here. And what the problem that we have in astronomy is that many times we have huge numbers. So when you have such a big numbers or a range of, for example, sizes or distances, it's very difficult to put all these things in your head. How can it be that big or that small or that large? And in this talk, my idea is to try to actually help you digest a few of those numbers as we discuss neutron stars. That is the main subject of this talk. Some of you might remember there was a very nice video 20-30 years ago. It was called Power of 10. If you don't remember it or you don't know about it, just search for it and you will find it. It was an amazing video where they were showing you the scales but now from the point of view from going from an atom to galaxies. And what I'm going to do now, if it works, is to go through 44 orders of magnitude in size in 44 seconds. That means that we're going to go from 10 to the 26, I think it's meters, to 10 to the minus 18 meters in nature. 44 orders of magnitude is basically 44 zeros next to the 1. And it's just a short part of that video, Power of 10. So the video starts just at the end when it's actually going away from the Earth. And what you are going to see in there, it's a circle. Every time that you see a circle, it's another 0 that you are taking away. Now you're adding it. And it's about to finish the zooming out. Now we're going to start zooming in this moment. And every time that you see a circle, it's 0. So every second, it's 1 0 that you are changing in size. Now we enter the solar system, the Earth, just a tree, a drop of water, and we go inside the water. And we go even inside the structure of an atom. And that was in 44 seconds, basically going 44 orders of magnitude from basically the biggest scales in the universe to the smallest scales in the universe. So it's a lot, and I think it's a lot to digest. Some of those scales, not as big, because of course as large, is what we're going to be dealing with neutron stars. So now it's when the talk starts. But I hope that you agree with me that these big numbers, if we don't put them into context, it's completely out of this world. So stellar evolution, you start with a cloud. I don't know if you see my mouse, but it's on the left. and then that creates a star. The star evolves, it goes into the supernova, and you have two possibilities. If the star is big enough, is that it ends up being as a neutron star, a very compact object, or a black hole. And as mentioned, we're going to talk about neutron stars, but what is important is that the evolution is very similar for the two cases. And the main difference is the original size of the star. If the star was more than 10, 20 solar masses, then you will have, up to 10 to 20 solar masses, you will have a neutron star, depending on the process that produces supernova. If you go larger than that as the original progenitor, then you don't have any other way to finish than it's not a black hole. Okay, something went wrong. So the first thing that I always like to talk about is whether it's an explosion or an implosion what produces the neutron star. And actually, while we always think about an explosion, the supernova is an explosion, what is important for the creation of the neutron star is the implosion part. And I give you an example. When you see a building collapsing, like I show in this series of images, there is a lot of dust going out, and you would, from far away, even think that what you are seeing is an explosion, but you know very well that what you are seeing is the building collapsing it itself. And while there is a lot of dust that it flies away, most of the material, or there is a lot of material, bricks, windows, etc., that ends up in a very compact volume that then they have to clean up. So in a supernova, that's basically what is happening, is that while there is a lot of things, a lot of material going out in the explosion, also there was a moment where there was a lot of material or gas that is compressed in the center. And that's the part of the implosion. And when that is compressed is where you reach the level of putting protons and electrons together to form neutrons, and that's why the neutron stars are called neutron stars. If you are in the area of a core that is between 1.4 to 2 something solar masses, you have a neutron star. If the core is more than that, then you end up with a black hole. The gas the material inside the neutron star cannot handle the pressure, the gravitational pressure, and therefore collapses into a black hole. So now is when the fun part comes, and the question is, how much matter is compressed when a neutron star is formed? So let's first just remember the scales. This is the sun compared to all the other planets, and this is in relative scale. So the sun is if the sun would be like that, we are there in a very, very, very small place. Taking that into account, the Earth would have to be compressed very, very, very a lot to have a neutron star. Now, if anyone dares to say how much you have to compress the Earth to have the neutron material, anyone dares to say how much you have to, in terms of scales, would you have to put it into the size of the United States, or the size of UK, the size of a ball? How much do you have to compress the Earth so that everything that is left are neutrons? Anyone dares?
Tennis ball.
Tennis court.
Tennis ball.
Sorry?
Tennis ball.
Ah, tennis ball. Okay. Someone else?
An atom.
Well, that's too small. That's too small, because it's a whole Earth into an atom. That's actually, I think, that too much. So basically, the Earth is into the size of a stadium. If you put the Earth into the size of marble, you have a black hole, just to give you more or less indicative sizes. So it is a lot. And I think that at this point, while you probably smile and say, yes, okay, you don't realize how much that is. It's really all the people, all the building, all the nature, all the mountains, all the water, and we are all that I just said is nothing compared to the whole structure of the Earth. And we still need to compress all that into the size of a stadium. That is the type of compression that we need. And that's why when we talk, in most of the talks in astronomy, when we talk about neutron stars, we compare it to the sun. And basically you have to put 1.5 more or less times the size of the sun into a sphere of diameter of about 30 kilometers. So this is, well, I live in Southampton, so that gives you more or less the idea here of how big is a neutron star, a real neutron star now. It's tiny, but it has the mass of 1.5 or even 2 times the sun. And remember, the sun is big compared to the Earth. Again, for me, this is a bit difficult to visualize or digest. So I brought another example, and it's how dense is dense and how much would it weigh a spoon of that material that is on the neutron star, and probably from the outside part of the neutron star. And basically what it is about 10 to 11 kilograms. And give or take, it's basically putting the weight of all humans on Earth on a spoon. That's basically it. So take a second. This is 10 to 11. So we are talking about 11 zeros there. It's a lot. It's a lot. And this is a real astrophysical object. It's that is completely extreme. You go a bit more, and then you have a black hole. So how fast? So we have a ball that is very, very, very compact. That ball, like any other star, rotates. So let's think about rotations and try to get an idea of what it means and how fast these things rotate. And then again, let's put it in context of things that we can visualize. So a ceiling fan rotates about 250 times per second, RPM, revolutions per minute. Sorry, revolutions per minute. So 250 revolutions per minute. You can actually look at it. You know that it's going fast, but yeah, it's not that fast. So we go to the next step. That can be a car wheel. So we're talking about a car going at 100 miles per hour. So that is fast. The wheel is making 1,400 turns, revolutions per minute. So that is fast. The washing machine does actually 2,000 RPM. And a kitchen blender is between 10,000 and 30,000 RPM, depending on how good the kitchen blender is. But the professional ones are between 20 and 30K, between 20 and 30,000 RPM. And I'm sure that all of you at certain point have actually looked at the kitchen blender and tried to see the blades rotating. And I have a very nice, funny animation, but of a blender in very slow motion. And what happens to eggs when they are in there? It is impossible to see the blade moving, even in slow motion. Wait, let me take out the sound because. Yeah, it is. You will agree with me that it's fast. And that is a very tiny thing. It's just the blades that are this size. So we were saying kitchen blender, 30,000 RPM. Well, a neutron star, the fastest one, rotates about 700 times per second, which is equivalent to 42,000 RPM. So let's say that you don't look at the fastest neutron star, one that actually does 30,000 RPM. So it's the speed of a blender, of the blades of a blender, but it's a ball of 30 kilometers in diameter, rotating at that speed. That is what for us is kind of natural astronomers to actually find this type of stars that are rotating at that speed. So many times I get a question, and probably I will get it later as well, and we can discuss it, but can you land on a neutron star? Of course, land is the wrong word to use, but you understand what I mean. So my general answer is yes, you can land on a neutron star, but basically this is going to be your fate. Because you are going to be falling on something that not only you have the problem of gravity, the problem of magnetic fields that we're going to talk about, but it's rotating super fast. And basically, yeah, what else do you want me to say? It's amazing. So they are also magnets. They are balls that become a magnet, and they have magnetic fields. And of course, one step backwards is not all the neutron stars rotate at the maximum speed. You have them at different speeds, but you can also have, just as an example, the typical, what we astronomers call slow neutron stars are the ones that rotate one rotation per second. That is what we call slow in neutron stars. So again, as a comparison, is like if our day on the Earth lasted 1 second, and fast is 700 times per second. So these neutron stars are also big magnets, and I will go again through some comparison. For magnetic fields, we measure them in some units that probably many of you are not used to, even if you have heard of it, but we use the word Gauss. And it doesn't matter what Gauss means at this moment. What is important is the relative difference between the different examples that I'm going to give you. So a human brain has a small magnetic field, and it has something around 10 to the minus 8 Gauss. That means that it's 7 zeros and a 1 after the dot. The Earth magnetic field is actually not that strong either. It's 0.3 Gauss. Okay. You have things in your house that have actually very strong magnets. Is the refrigerator, for example, has a magnet that is about 50 Gauss, and of course there are lots of fridges, but as an average one or representative one, it's 50. So already, if you look at these numbers, between the magnetic field of your refrigerator and the human brain, you have 9 zeros difference. If you go and have to get a medical magnetic resonance at the hospital, those ones, if any of you had to go for it, you will remember that they will tell you, we'll ask you 100 questions about whether you have any metals in your body, in your tooth, if you have piercing, you cannot use glasses, if you have earrings, anything, because that is really a very strong magnet. And actually, basically, and again, as a representative number, the magnets in those MRIs have a power of magnetic field of 30,000 Gauss. So now we're talking about 10 to the 4 Gauss. So again, it's 12 zeros in difference between the magnetic field on your brain to one of those in a MRI. So you might wonder what is the strongest magnetic field that we humans have accomplished here on Earth. This is the only thing I could find online, and it says that the strongest non-destructive magnetic field, and I'll come back to that in a second, is about 100 Tesla. Where 100 Tesla is, it's a million Gauss, so it's 6 zeros. It says non-destructive because we have managed to get higher magnetic fields, but the whole lab or whatever you were producing it exploded. It got completely destroyed. So the strongest magnetic field that you could get in a lab and not have the whole lab disappear is of about 1 million Gauss. As you can imagine, that's nothing compared to a neutron star. So Tesla, 1 million Gauss, a neutron star, the bad ones, the real heavy ones, can have magnetic fields that are as high as 10 to the 15 Gauss, more or less. Give me a second. Okay. Okay. Yeah. Sorry about that. So it's 10 to the 15 Gauss, a neutron star, and there are many of these ones, 10 to the 15, 10 to the 16. That is 9 more zeros than, so 9 orders of magnitude higher than the strongest magnetic field that we could produce on Earth without making the lab disappear. I have been struggling to have an example of how you visualize that, but it's just so large, so large. Even the neutron stars that we consider weak, with weak magnetic fields, if you read papers, you say, oh, that neutron star has a very weak magnetic field. It's still 1 or 2 orders of magnitude higher in terms of a magnetic field than what we can produce in Earth. So that's the extreme. So you have a very small sphere that rotates very fast, that has a very strong magnetic field. How do you study them? So astronomers, we need to find a way to be smart and try to do it. Here, I'm going to give you a few examples of how we do it. But depending on whether you study them in radio or in X-rays, gamma rays, even optical, the techniques change and the way that we extract information is different. So in my research, what I do is to look for neutron stars that are part of binary systems. If the neutron star is very close to a star, like our sun, at certain point, gravity, they are so close to each other that the gravity of the neutron stars start pulling, stealing gas from the companion. That gas flows and needs to spiral onto the neutron star, forms a disk, and that gas that flows on the disk slowly falls on the neutron star. That gas has to interact with a neutron star that is rotating very fast. It has to also interact with the magnetic field, and of course, and I will show it again. And depending on how strong the magnetic field and how fast it's rotating, you will see different phenomenology. We're not going to see exactly the same thing. If you are lucky, the neutron star will pulsate and become a pulsar, but not all neutron stars are pulsars. And one reason is that they are pulsars, but they are not pointing at us. but basically 85, in the case of observations of this system, 85% more or less of the neutron stars are not pulsars, which is very difficult to explain. Again, to give you an example of how extreme things can be, this is in scale, and what you see here is the Earth. On the top left, a white dwarf that is being eaten by a neutron star. The whole system is tiny, tiny. It's in comparison with the sun that is on the bottom. And this system that has the name 4U1820-30 has an orbital period. So the white dwarf goes around the neutron star in 11 minutes. That's the orbital period of that white dwarf around the neutron star. 11 minutes. It's like, again, if the Earth would do it, we do it in a year around the sun. Imagine if it was every 11 minutes. For those that are interested, the name of the source is basically the coordinate, a combination of the coordinates and the first satellite that found it. 4U, U is for Urururu or something like that. Some decades ago already. This is a bright system that has been active for a long time. Active means that for a long time gas have been accreting, falling into a neutron star. And the coordinates are 18 degrees 20 minutes minus 30 degrees in declination. And we are lucky that there are not so many sources, X-ray sources in the sky. Therefore, you don't need too many digits to know where they are. Of course, when you need to point the telescope to it, you need all the digits. You need the degrees, the minutes, the seconds, etc. But in terms of coordinates, this is more than enough. And how do we study them? Well, because the gas is flowing slowly, it goes slowly from the outer part of the disk to the inner part of the disk. As it goes into there, there is friction. You can think of this disk as being composed of many rings, concentric rings, and each ring goes at a different speed, and therefore there is some friction between those, and it becomes hotter and hotter. And when you reach the area or the space very close to the neutron star, the temperature are of millions of degrees, which translates into X-rays. So we need to observe it in X-rays. X-rays don't arrive to Earth because we have the atmosphere. Sorry, they arrive to Earth, but we cannot observe them from here because of the atmosphere. That's good for us. So we need to use X-ray telescopes. And these are 3 examples of the things that I use in my research. And the top is called, NuStar. This is called XMM, Newton, and this is called Chandra. So we need to use those telescopes to actually study the things that happen very close to the neutron star, where the areas are very, very, very hot, X-rays. One of the things that I like the most and I find more impressive is what we call thermonuclear X-ray Girths. So these are explosions that happen on top of the neutron star surface. The way they happen, and I'll show you a movie in a second, is that gas flows from the companion star, hydrogen, into the disk, and from the disk onto the neutron star surface. And you start accumulating this hydrogen onto the surface until a point that the gravitational pressure and the temperature is so high that actually you ignite a thermonuclear reaction. The same reactions that are produced at the core of the sun, now they're happening at the surface of the neutron star. And then the whole surface of the neutron star burns in a second. So this is an animation in very slow motion of that ignition that happens somewhere on the neutron star, and then within a second covers the whole neutron star. And this is very, very slow motion. That explosion can interact with the disk. And this is, again, I don't know if you can see it well, but at a certain point that neutron star will explode the surface. And as you can see, the disk moves out because it feels the radiation pressure from the energy that is produced on the neutron star surface and pushes the disk away, and the disk comes in. So this is kind of a fight. The disk wants to come in, but all this energy is pushing it away. All these kind of observations, all the observations of this kind of phenomenology is what allows us to study how gas flows around the neutron star, how fast it is put on the neutron star. It allows us to understand thermonuclear reactions without having to put bombs in the middle of the sea, etc., etc. And now, kind of almost finishing with one more comparison. This thermonuclear X-ray burst that I was mentioning lasts for about 20 seconds and happen very often. In some sources, you can see, in some systems, you can see one every hour. And thank God that they are far. In average, because there are many types of thermonuclear X-ray bursts, and we can talk a full hour about the different types of explosions that you can see. But just taking one representative, the energy emitted in one of these explosions is equivalent to, and this is just taken from somewhere, 115 megaton hydrogen bombs exploding simultaneously over each postage stamp size patch of the neutron star surface. A lot. Trust me when I tell you that is a lot. To put it in different ways, but in a different way, I like to put this because some people have research on what is a hydrogen bomb and what is a megaton hydrogen bomb. In this burst, it released more energies in 10 to 100 seconds than our entire sun in a week. So again, in a week, our sun, as you can imagine, emits a lot of energy. Well, on the neutron star surface, that is emitted in that explosion that lasts 10 to 100 seconds. So to be concluding, I could keep going and show you more weird things that happen on the neutron star, but if I learned something with experiences that if they teach you too much or they tell you too much, then you don't remember anything. So I prefer to stop here. The conclusion or the message that I want you to take is that neutron stars are very cool to study, very hot in reality. And there is a lot of very interesting physics going on that we cannot test in Earth. We will not be able to make it, not in now, no in 10 years, probably not ever, to produce them on Earth. And with that, I stop. Thank you.
Thanks, Diego. That was very interesting. Diego, what is our closest neutron star? Have we got one relatively close, I mean?
Yes, definitely. I would have to check because I know of the neutron stars that are in binary systems. So of neutron stars that are in binary systems, it's about between 1 and 2 kiloparsecs. And that's a lot of, let me think, like something like 10,000 light years or something like that. I would need to do the proper calculation.
No, I was just wondering if one was fairly close, if these things were going off, as you said, it could get a bit scary for us.
Oh yeah, actually, we are lucky that we don't have any of this close enough. So we see them we detect them very well. The moment that actually they put the first X-ray telescope in space, they found them because they are very, very bright, as you can imagine, but they are still far away, far enough that they don't affect anything on Earth.
Right. Well, the floor is open if anybody else wants to cover it.
I've got a question.
Yeah.
The compression that causes the creation of neutron star. What actually is compressing? Is it that the atoms within the body are getting close together, or are the subatomic particles within those atoms getting closer, or is everything getting closer to compress?
So the magic word is gravity. So what you are having in every star, you have two forces acting to maintain the equilibrium. You have gravity that is pulling down or pushing down, depending on what you want to say it, but it's basically everything wants to go in this direction. But in the sun, just as an example, you have the nuclear fusion that is producing energy that pushes things out. So the sun, as it is in a stable configuration because the force of gravity is the same as the force of all the energy that is produced on the center. Of course, it's a bit more complicated, but that's the idea. When the stars evolve, you reach a point where, sorry, let me go to, so imagine that you have a star that is only hydrogen. You start with that. At a certain point, you run out of hydrogen in the center because you have mainly helium. So to be able to fuse helium into something heavier like carbon, the whole star undergoes a transformation where things collapse because you run out of the other force that was maintaining the star, compresses everything until helium starts burning, and then you have a new equilibrium. That process continues until you have iron. When you have iron or a base, is iron? Yeah, in the center, there is no way that you can fuse that. And therefore there is nothing to stop it collapsing. So now depends on which is the size of the original star. If the star is small like the sun, actually it will compress, but it will not collapse. Atoms will get very close to each other, and it will just stay there, cool down, and become a brown dwarf, I think it's called, or some other color, just cools down. If it was much bigger than the sun, it collapses and it needs to collapse. The pressure is too much. And there is where you start putting protons and electrons together to form, in spaces that are close to a neutron. And that's where you have basically the supernova. The thing cannot keep itself, but it has to, you have to have the implosion that produces a supernova and leaves you with a neutron star or a black hole.
Right, thanks.
Yeah, there you go. If the if the neutron star, as you showed, is sucking in material from a binary partner, is it possible that it achieves an equivalent mass to that which would have been required for it to become a black hole?
Yes.
So can a neutron star evolve into a black hole by that means?
The answer is yes, and it is expected that that would happen. It would be amazing to observe it, but it would be something rare because you have to, it takes a lot of time to actually put enough material on the neutron star until it reaches the limit where it collapses. So most probably you would need to have, you need to be lucky that you produce a neutron star that was already very heavy, We don't know exactly where the limit is, but it's something like 2.5 solar masses. So for the sake of the argument, let's say that the limit of what gas, what matter can hold before becoming a black hole should be, let's say, 2.5. So you would need a neutron star that is born just at the limit, and then that the star next to it gives enough gas to make it past that limit. But indeed, it is possible.
So are there other fates for neutron stars? If one fate is potentially becoming a black hole, what are the other?
The other one
outcomes?
is just to cool down and disappear because we cannot see it, as a very slow, cold neutron star. Flying. It's a ball, very dense ball of 30 kilometers in diameter, just flying in space.
But that's not the same as a red dwarf or a brown dwarf. That's a very dim star. Is there still nuclear fusion occurring, or is it?
No. In the neutron star, you don't have any more nuclear fusion.
Okay.
It's basically reach an equilibrium where everything holds. It's like all the whatever particles. So, okay, let's go a step backward. We call it neutron star because that is the expectations, that you put protons and electrons to get so close together that they produce neutrons. But one of the probably fundamental questions of physics, atomic physics right now, and as high energy astrophysics, is to understand what is that we have inside the neutron star just before it becomes a black hole. And definitely it's not they are not neutrons, it's something else. So what people are trying to do is estimate what is called the equation of state of density of the neutron star, and that will tell you what type of particles you will have inside, because definitely we will never be able to go and make a hole on the neutron star. But we can model, based on our understanding of particle physics, model different scenarios, and in that way imagine what you have inside the neutron star. But definitely you are not having thermonuclear reactions inside like what you have in the sun.
So the star is effectively dead at that point. That it's reached an equilibrium which balances gravity with what heavier elements, which, I mean, if there's no thermonuclear reaction outwards, how does it maintain that stability? Is it like an ember, a fire, which is not quite a fire, but
no, but you have the pressure that the pressure of the basic particles that they want to repel each other.
Oh, I see.
So, but that you compress it a lot, but they are still trying to keep.
Yes.
Yeah.
Okay.
So if I'm correct, is it the strong nuclear force that is has an impact within atoms, keeping particles together, apart, however that works? What is that right? And what impact is there on that force when it gets down to being a neutron star?
Actually, I'll pass this one because this is my understanding is that it's more complex than just the ones that we know.
Right. Okay.
And that's why you will read in the news or in papers that they call they sometimes they need new type of particles or these new type of interactions to be able to understand how the neutron star keeps together. Because there are some, so basically you have situations where you say, okay, let's assume that the inside of a neutron star is this type of particles. So that will tell you that the neutron star, for example, could never be larger than 1.2 kilometers in radius. So so if that 1.2, yes, 12 kilometers, sorry. So if you find a neutron star that is 20 kilometers in radius, then you know that you cannot, that whatever you type of particles you invoke and the forces that you invoke, it cannot be, because you have a neutron star that is bigger than that. The problem is that you have literally hundreds of these models, and they are very close to each other. So to be able to differentiate between one model and the other one, you need very precise measurements of the mass and of the radius of the neutron star at the same time. So only the radius or only the mass doesn't, it does help, but it doesn't solve the problem. You need to have one system at least where you can measure the two very, very precisely. And very precisely means 15 kilometers plus minus 2 meters. It is really precise.
So basically, there's some pretty exotic physics going on when you get down to that sort of level.
100%.
Yeah.
Yeah.
You mentioned pulsars earlier. Can you explain the connection or the difference between pulsars and neutron stars?
No. So neutron stars can be pulsars or not. So it's an effect that happens on the neutron star. Give me a second, I'll be right back.
The perils of having children.
Yes, I'm still admiring the pink elephant on the back screen.
He did tell me that he had a young child and it might be interrupted, so that's fine.
Okay, I'm never gonna. Yes, indeed, I'm having children. So what was the question? Pulsars and neutron stars. So all the neutron stars are rotating. If you have a rotating sphere, which has suddenly a lamp on it, it becomes a lighthouse. And that is what we call a pulsar. It's a lighthouse that is, from the geometrical point of view, it is a lamp on the neutron star, and the neutron star is rotating. So you see the light every time it rotates. Does that make sense?
Yeah.
Yeah, okay. So
Yeah, but how does the lump get there? I suppose.
Yeah, exactly. Well, that was the second part. First is understanding what a pulsar is. So the pulsar is it's a neutron star that is rotating, that has a lamp, and now it's the important question: if the lamp is pointing up and the neutron star is rotating like this, you will never see the pulsar because it's not pointing at you. So you have to have the lamp pointing in your direction, otherwise you are not going to see it.
But Diego, what is what you are describing as a lamp? What is that?
No, I know, I'm getting there. Sorry.
Okay, sorry.
Don't spoil the story.
Sorry, I'm sorry.
Punchline's coming.
Okay.
Yeah, okay. So because it answers, I need it. Trust me, I'll come to that.
Okay.
So we have a rotating sphere that it has a lamp, because the original question is, what is the difference between a pulsar and not pulsar? So the pulsar is when you actually see that lamp. But the fact that you don't see the lamp, it doesn't mean that it's not a pulsar. It can mean that it is a pulsar and you are not seeing the lamp. Now, so that is the main difference. Now, what is that produces the lamp? In the case of the systems I study, that are neutron stars in these binary systems, the neutron stars have magnetic fields. These magnetic fields is as you imagine a magnet, that it looks like this. When the disk comes in, interacts with the gas, and these magnetic lines pull gas and put them into the magnetic poles. That gas that falls on the magnetic poles makes the magnetic poles hotter than the rest of the neutron star. And if it's hotter, is basically like if it was a lamp.
Okay.
Yeah. But again, you can have the pulsar mechanism working, you can have the lamp, but you don't see it.
Sure. Because it's not pointing in the right direction. Yeah.
Exactly.
Can I ask a question about the magnetic field and how it's generated? I think most of the people watching tonight know that the Earth has a magnetosphere and a magnetic field generated by a metallic core which rotates with the Earth. And another example would be Jupiter, which rotates, of course, very quickly and is supposed to have also a metallic core. And that generates, like a dynamo, a magnetic field. How is it? Are we saying that in a neutron star there is a metallic core as well, even in such a small object?
Yeah.
Okay.
It's not metallic, but it's the same idea.
Can you elaborate? Can you?
Well, you have I'm trying to think if I can explain it in very simple terms without going into too many details. Let me think about it. I'll come back to that later.
Okay, but I mean, but basically it's the rotational speed, the very fast rotational speed, which is still producing that dynamo effect, is it, to produce the magnetic field?
Yeah. Yeah. Well, no, but the magnetic field is part of the neutron star independently of whether it's rotating.
Okay.
Because it is believed that you had the star, the original star, had a magnetic field already. And then basically you compress a lot of that material into the neutron star, and that enhances the magnetic field in the object that you have left.
Okay.
So it's not that if you stop the neutron star, the magnetic field would not be there. The magnetic field is part of the system and how it was created.
Sure. Okay.
Am I correct in thinking that the origin of the fast spin speed is sort of conservation of momentum when the object collapsed on itself? Is that the?
Yes and no, because there are two ways that you can reach that. So to elaborate on that, so if because of a conservation of angular momentum, conservation of this thing that we call angular momentum, if you have a star that is rotating slow and suddenly you compress it, then the star will rotate faster. And this is basically when you see a dancer on ice, that they jump, they get smaller, they rotate faster, they expand their arms, and they rotate slower. So that's what James was saying. And indeed, that is what's happening. However, you have what is called the recycling scenario. So imagine that you form a neutron star on the supernova. That neutron star rotates very fast, but it's lonely, alone. Nobody interacts with that neutron star. So it will lose energy and it will slow down. And it can slow down to, for example, from maybe 1,000 times per second or 700 times per second to 1 time per second, or even less. Now, that is what is called an all-neutron star. Now that neutron star finds a partner that is the companion star, the sun, and starts stealing gas, or absorbing the gas from the other. That gas is going to transfer angular momentum onto the neutron star. And then you suddenly can speed up the neutron star again. And speeding up, you can speed up to very high speeds. I'm not sure whether it's the same speed as the original one, but definitely very high.
So the speed can increase, decrease, depending on what else is around it.
Exactly.
Right, okay. And am I correct, coming back to what was mentioned about pulsars, am I correct in thinking pulsars have a steady spin speed, so they don't vary?
No, actually,
do?
it does change. And again, here it's two different subjects. If you talk about isolated pulsars, these that are generally studied in radio, or the pulsars that I studied that are the pulsars that you see because there is gas lighting the lamps. Because there is gas interacting with the neutron star, therefore it's going to make it go faster.
Right.
When there is no gas falling on the neutron star, in theory, then the neutron star is kind of losing only energy, so it's slowing down. So what you would see is kind of going up and down. And definitely something that has been observed.
Thank you.
Great. Any more questions?
Well,
Mark?
I was going to pose one.
Yeah.
I was intrigued about the conversation earlier of how it's a dying ember and it's just going to get cooler and cooler until it disappears. But I imagine it's over a colossal time. So in the time of the universe, will that have happened? Will any neutron stars have formed and be cool enough to be unobservable, or is it such a colossal timescale that?
Oh, no.
It's
There are many neutron stars that we are not able to observe because they are too cold. Still, cold might be quite hot, but if you take into account that they are far enough, you don't know where they are, and then they are difficult to detect. How cold they can become, they can, in theory, they can become very cold. How long it takes to become whatever temperature you think of, I'm not an expert, so I wouldn't know. But definitely, if the main thing is, if the neutron star does not interact with the environment, so it's really lost in space, then the only way possible is just keep losing energy, cooling down, and that's it, and end up as a rock lost in space.
Oh well, so I'm still looking for a real reason for dark matter and dark energy. I'd love it to be something that's real rather than a theory.
Well, again, not being an expert, so I need to be very careful what I say. But one of the theories of dark matter is that it's a lot of or it was back then, I think it's proven that it's wrong, but that it was a lot of small black holes that are flying away and you cannot see them, they are too cold, so that's it. But I think they found a way to say that that's not possible for some other reason, but I'm not an expert at all.
So Diego, are we saying that neutron stars have existed, the ones we observe now, well, obviously there's no such thing as current because everything is light years away, but there are multiple generations of previous neutron stars, which we think have now died, but we can't see them, but they are there in time. Okay.
And some of them, we suddenly start seeing them again because they start interacting with another star, for example.
Oh, I see. Yeah. Because of their mass, and they then accrete. Yeah.
Well, no, because space is big, so the chances that a neutron star interacts with another star are slim.
Remote.
But if you are in a globular cluster, for example, where the density of stars is very high, then if you have a neutron star there, which there are many, there are very high chances in time, not in 100 years, but
but in stellar time, yeah.
Stellar time, that they find another star and they start interacting.
They basically bump around like billiard balls and find something else to, yeah.
It's a way to see it, indeed.
Yeah. Okay. Fascinating. Mark.
Yeah. Diego, thanks very much for a really interesting and detailed talk. Can everybody show their normal appreciation of such an excellent presentation
Yeah, thank you.
by